constant mass method. Let us solve the previous problem by a constant mass method. Constant mass means mass of the system should remain unchanged. The mass of the system does not vary with respect to time. Accordingly, you have to choose the mass. If you choose the system the hopper plus trolley car, then the mass of the system does not change. If you choose the hopper as a system, the hopper is losing mass because the sand is continuously coming out of the hopper and hitting or colliding on the trolley car. Therefore, hopper alone cannot be a constant mass system. If you take the trolley car as a system, it gains mass due to the loading sand. Therefore, the trolley car cannot be regarded as a constant mass system. However, if you take the hopper plus trolley car as a system given by the dotted line, enclosed by the dotted line, mass of the system remains constant. Once you choose the system, constant mass method will work. Choosing of the system is first. Then apply impulse momentum formula, which states that the net force acting on the system, its time integration, or net impulse equal to impulse of the net force along horizontal direction is equal to change in momentum of the system along horizontal direction. We are applying the impulse momentum equation of the system of constant mass. The system is hopper plus trolley car along horizontal direction, which states that the impulse of the net force, that is this applied force. You cannot take the impulsive force or the impact force. Impact force may be acting on the trolley car, and same impact force or impact force of the same magnitude is also acting on the hopper or the sand falling on the trolley car from the hopper. As a whole, this impact force for the system hopper plus trolley car is an internal force. This impact force, one impact force is acting on the trolley car, another impact force is acting on the colliding sand particle in forward direction or in positive x direction. Therefore, impact force as a whole will be 0 on this system of constant mass. Hence, the net force acting on the system along the horizontal direction or along the positive x direction is plus F. So, impulse of this net force is equal to change in momentum of the system along x direction. This is equal to final momentum of the system along x direction minus initial momentum of the system along x direction. The net force is Fi cap, its time integral is equal to, initially the momentum of the system along x direction is equal to mass of the trolley car into velocity of the initial velocity of the trolley car, that is pointing along positive x direction, because it is moved with velocity v naught towards the right initially. This is the initial momentum. The final momentum of the trolley car along positive x direction will be equal to its initial mass plus the mass of the sand gathered onto the trolley car into its velocity, let be v, after time t. Finally, along which direction? Positive x direction. And the hooper along with the sand particle cannot have a momentum along x direction, because hooper is stationary and the sand particles are moving vertically downward. Therefore, the final momentum of the system along x direction is this much. Initial momentum of the system along x direction is this much. This is the change in momentum of the system along x direction. If this force is kept constant, take it out of the integral. So we are getting this term is equal to m plus mu t into v minus m v naught. So next step is very simple. This factor will be equal to f into t is equal to m into mu into m plus mu into t into v, m plus mu t into v minus m v naught. Finally, you are getting the result ft plus m v naught by m plus mu t. Same result we got in the previous procedure. There we got the velocity, exactly same quantity. And if the initial velocity is 0, the velocity of the trolley car as the function of time will be ft by m plus mu t. And acceleration, so once you get the velocity, taking the derivative of the velocity, you can get the acceleration, your desired quantity. So this is a process of constant mass method. Using this, by using impulse momentum equation, you can get the same thing. Taking the foregoing problem into account, if the trolley car is required to move with constant velocity, find the actional force that is equal to Fc. Find the power delivered by the external agents who is pushing the trolley car with constant velocity. Find this change in kinetic energy of the trolley car, and also find the loss of energy in terms of heat, sound, etc. per second, or we can call it power loss. We can solve it by impulsive force method by drawing the free body diagram on the trolley car. Here we can have two forces, as I discussed already. One force is the external force or the applied force or the force F. You are pushing the trolley car. Another force is the impulsive or impact force acting on the trolley car. The net force acting on the trolley car is F net is equal to F minus F impulsive. That's equal to F minus F impulsive is equal to mu into V, as you calculated in the previous problem. Since velocity of the trolley car is kept constant, the acceleration of the trolley car is equal to dv by dt must be equal to 0. According to Newton's second law, net force is equal to mass times acceleration. The net force acting on the trolley car is F minus mu V, and the acceleration of the trolley car is 0. This will give us the magnitude of the applied force, that is equal to mu V, exactly equal to the impulsive force and oppositely directed. Answer. So this is the answer of the first part. Come to the second bit. We are required to calculate the external power. This is the external force. The external power or the power delivered by the external agent is given as the dot product of the external force and the point at which the external force is acting. What is the velocity of this point? That velocity. So the power delivered by the external agent or the external power is equal to external force dot the velocity of the point of application of the external force. This point moves in this direction with same velocity. These two vectors are unidirectional, therefore their dot product will be equal to F external into V. The angle between these two vectors is 0, cos 0. That gives us a positive power. And what is F external? That is equal to mu into V, as you calculated. So we got the result of the second bit. which is equal to mu times the square of the velocity of the trolley car. Now come to the third bit. In the third bit, he is asking to calculate the rate of change of kinetic energy. Here the velocity of the system is kept constant, whereas the mass of the system is varying, is increasing at a rate of mu. Let us assume that m dash is the mass of the system, that is trolley car plus the loaded sand. When it is multiplied with half of the square of the velocity of the trolley car, we are getting the kinetic energy. And what is m dash? M dash equal to initial mass of the trolley car, or mass of the trolley car into the loaded sand mass. Mass of the loaded sand during time t, that's mu t. So m dash equal to m plus mu t, half will be there, and multiplied with the square of the velocity, and this gives us, since this is a constant quantity, this gives us mu v square by 2. It is interesting to note that the rate of change of kinetic energy is exactly equal to the 50% of the external power. This physically signifies that 50% of the energy supplied by this external agent onto the or to the system is utilized in increasing the kinetic energy of the system. That is mu v square by 2. You are supplying energy at a rate of mu v square. And what happens to the next 50% of energy? Obviously, that is getting away, going away, that is dissipated in terms of, or in the form of heat, sound, light, etc. Then we can write the power loss or loss of energy per second is equal to power input, that is the external power, the power delivered by the external agent onto the system, minus the rate of change of kinetic energy. This is in accordance with the conservation of total energy, mechanical plus the dissipated energy. So this gives us mu v square minus mu v square by 2, that's mu v square by 2. 50% of the input energy is dissipated or lost in the form of heat, sound, etc. That's very interesting. If you think that the velocity of this system is constant, therefore its acceleration is 0, therefore this force is 0, but actually this force is not 0. The net force acting on the system is 0. The net force is F minus impulsive force, that is 0. When you equate these two forces, you are getting the net force 0, or you are getting the applied force, or the pushing force is equal to the impulsive force. And using that, all these answers you can get one by one. That's a nice problem. The context of conservation of linear momentum. When no net external force acts on the system, the momentum of the system remains conserved. For instance, you take the trolley car, let us assume that you are standing on the trolley car. Your mass is small m and mass of the trolley car is capital M. If you jump horizontally with the velocity u with respect to the trolley car, We can calculate the velocity of the trolley car by using the conservation of linear momentum. Find velocity of the trolley car just after you jump horizontally with the velocity u relative with respect to the trolley car. That's a basic question. Now we have to choose the system in such a way that the net force acting on the system must be 0. For the sake of simplicity, ignore the frictional force between the trolley car and ground. But you cannot ignore the frictional force between you and the trolley car, because you are using that friction for jumping. If there is no friction between you and the trolley car, you cannot jump. While you are jumping, you don't slide with respect to the trolley car. The trolley car will push you towards the right with a force that is none other than the static force of friction. And at the same time, you can push the trolley car with another force which is equal and opposite to the force you are getting from the trolley car. So these two frictions act, one on you, another on the trolley car. This is plus F, this is minus F. What is the net force acting on the system? 0. The net force acting on the system is 0 on the horizontal direction. Plus Fs plus minus Fs equal to 0. When the net force will be 0, then the momentum of the system can be conserved. This is the analysis part to ensure that you are going to conserve the linear momentum of the system containing the trolley car and yourself. Then you can write momentum of the system finally must be equal to momentum of the system initially. You can write 2 or you can write F. You can write 1 or you can write I. It's your choice. Since initially you are at rest, the trolley car was also at rest. Momentum of the trolley car and your momentum, both the momenta are individually 0. Therefore, the initial momentum of the system is equal to 0. P1 is equal to 0. Now let us calculate the final momentum of the system. Individually, let us calculate the final momentum. When you are jumping with the relative velocity u relative, you are getting an impulse of this friction, And the boat also is getting an impulse in opposite direction of equal magnitude in backward direction. Because of this impulse, the boat will change its momentum from 0 to a certain value. Let it be velocity, let it be momentum of the boat PB. Due to the impulse, you are changing the impulse, you are changing the momentum from 0 to a certain value. Let it be PM. M stands for man, B stands for boat. Your momentum is PM, momentum of the boat in backward direction is PB. If you sum up both the momenta with respect to ground, you are getting the final momentum of the system. Momentum of the man or your momentum is equal to your mass small m into your velocity, let it be Vm with respect to ground, plus momentum of the boat is equal to mass of the boat, that's capital M, into velocity of the boat with respect to ground. Once you get the final momentum and initial momentum, you have to just equate these two momenta using the concept of conservation of linear momentum. So substituting P2 and P1 in the equation 1, we are getting MVM plus MVV is equal to 0. That is equation number 1. We have to take the help of Galilean transformation of velocity, which states that velocity of man with respect to ground is equal to velocity of the man with respect to the trolley car, or we can call it boat, plus velocity of the boat with respect to ground. This is the equation number B, Galilean transformation of velocity. This is the concept. And this one is the concept of conservation of linear momentum. We are using two concepts here and substitute the value of Vm, the velocity of man with respect to ground, from equation B in equation A to get m into velocity of man with respect to the boat plus velocity of the boat plus m into Vb is equal to 0. And next step, you are getting velocity of the boat is equal to mass of the man into the velocity of the man with respect to boat by mass of the boat plus mass of the man negative of that. Since you are jumping with the velocity u relative with respect to the boat, this factor will be equal to u relative. Whose direction? I cap direction by m plus a. This gives us both magnitude of the velocity of the boat and direction minus I cap, that is backward direction. This physically signifies that the boat is recoiled back with a velocity small m into u relative upon capital M plus small m. Answer. You can pose next question. What is the work done by the man? How much work you are doing when you are jumping out of the boat? Work done by man. Next question. What is the work done by you? You have to apply the concept of work energy theorem, because this system is not a conservative system. When you are jumping, you are losing energy, and our body is not a conservative system. Therefore, we need to apply work energy theorem for system of particles, which states that work done by the non-conservative force plus work done by the conservative force is equal to change in kinetic energy, but the conservative force does the work at the expense of its potential energy. Therefore, work done by the non-conservative force is equal to change in potential energy plus change in kinetic energy of the system of particles. Here the non-conservative agent is yourself. So work done by the external agent is equal to change in potential energy plus change in kinetic energy of the system, that is man or you plus boat. Here when you speak about the potential energy, that is gravitational potential energy. Since you are jumping horizontally, you are not changing the gravitational potential energy just before and after the jumping, and the boat is constrained to move in horizontal direction, in horizontal line. Therefore, it's not also changing the gravitational potential energy. Therefore, this factor will be equal to 0. Then we can write the external agent, I mean you, are doing work which is equal to change in kinetic energy of the system. This kinetic energy change has two parts. There are two persons here. One boat is changing some kinetic energy, and you are also changing some kinetic energy. So how much kinetic energy you are changing and how much kinetic energy the boat is changing, if you add them both, you are getting the amount of work you are doing, and that's equal to half your mass into your velocity with respect to ground, square of that. And initially your kinetic energy was 0. So change in kinetic energy is equal to your kinetic energy just after jumping plus change in kinetic energy of the boat is equal to kinetic energy of the boat just after jumping of the man. The boat velocity with respect to ground is Vv square of this. Just you can substitute the value of Vm and Vv. Vm is equal to velocity of man with respect to boat plus velocity of the boat square of this plus half m, and Vv equal to small m upon small m plus capital M into u relative, just we calculate it. Here velocity of the man with respect to boat is u relative, that's I cap, and velocity of the boat is equal to m u relative I cap minus by m plus m. So if you add this two, you are getting m into u relative by m plus m square of this plus half m into small m u relative by m plus m. Just after simplification, you are getting work done by the external agent is equal to half small m into capital M by small m plus capital M into u relative square or u square. Answer. This is the work done by you. While you are jumping, you are doing work in increasing the kinetic energy of the boat and your kinetic energy of your center of mass. So in this way, we applied work energy theorem, the impulse momentum equation, conservation of mechanical energy, conservation of linear momentum. Using all these ideas, we are completing this great chapter, system of particles, which is the basics or form the base of the forthcoming chapters. These are rotational mechanics, the mechanics of fluids, liquids and gases. And these principles will be ultimately useful in understanding the concept of the flux velocity, the RMS velocity, and the internal energy. The internal energy is defined as the energy of the system measured with respect to the center of mass. In heat and thermo, we will discuss the concept of internal energy as the energy of the particles measured with respect to the center of mass of the system. That may be the kinetic energy of the system of particles with respect to center of mass plus. If at all there are some forces of interaction, they may give rise to some potential energy of the respective force fields. We should take that potential energy into account, and the potential energy of interaction between two particles, if you take as a system, does not depend upon any reference frame. Therefore, the internal energy, it may be a potential energy of interaction or the kinetic energy of the system of particles with respect to center of mass does not depend upon any other reference frame. Therefore, the internal energy, which is the sum of internal kinetic energy and internal potential energy, does not depend upon any reference frame. In other words, we can say that the internal energy is a property of a system. It does not depend upon any outside frame, any outside reference point. So, saying all this, I should take a pause, and next class we will start the new chapter. Thanks all of you.